तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Right, so I promised to do discuss Lorentz invariance and the associated 4 vector formalism a little systematically. So let me do that, and we start off with as follows. We start by saying that experiment has told us that special relativity's postulates have been verified now for over 100 years, and I wrote down the principle of relativity and the postulate of relativity, and they followed from the fact that if you have two space-time events, you have a space-time event occurring at a space-time point x mu, which is x naught equal to ct at some instant of time t in a frame of reference, and then x1 equal to x, x2 equal to y, x3 equal to z. I use this notation now, the superscript index notation. Then we know that this quantity here x mu, we know that this quantity c squared t squared minus r squared, which is the square of x squared plus y squared plus z squared, the sum of these squares, this is the same in two frames connected to each other by a Lorentz transformation. So we have the invariance of this quantity. This leads to the rest of what is going to follow, and it is convenient now, just as we defined a 3-dimensional vector as a set of 3 quantities which transformed under rotations of the coordinate system in the same way as the coordinates themselves did, that was our definition of vector. We now define a 4 vector as a quantity which transforms like x mu under Lorentz transformations, which would include rotations of the coordinate system as well as velocity transformations or boosts from one inertial frame to another. Now a little bit of notation here is helpful, so we are going to introduce this notation. And the most important thing that one would like to introduce is this quantity. So this thing here is a 4 vector, it is the primary instance of a 4 vector. So anything that transforms like this transforms like a 4 vector. Okay. Now this quantity g mu nu is called the metric tensor, and its numerical value is the following: g00 is +1, g11 equal to g22 equal to g33 equal to -1, and g mu nu equal to 0 if mu not equal to nu. All my Greek indices mu, nu, sigma, rho, etc. will run from 0 to 3. 0 is the time component, 1, 2, 3 are the space components. Okay. So this metric tensor and its analog, the downstairs metric tensor, I will explain what is meant by putting indices downstairs, equal to g mu nu component wise. In the flat space time we are talking about, where special relativity is valid, it is useful to introduce this quantity g mu nu called the metric tensor. There are 2 versions of it. There is a version with superscript indices and there is a version with subscript indices. We will become familiar with these, the distinction, in a short while. But as far as the tensor g mu nu is concerned, these are the numerical values. So g00 is also +1, g11 equal to -1, and so on. Now the reason for writing this is because in general it turns out that when you have manifolds, namely spaces with smoothness properties at different points, then the square of the interval between 2 space-time points in this manifold can in general be written down as G mu nu dx mu dx nu. This is a general statement here. A whole class of spaces exists called Riemannian manifolds, for which the infinitesimal separation between 2 points in this manifold, the square of that separation, can be written in this form. It is a scalar and can be written in this form here. Dx mu is the increment in x mu, dx nu is the increment in x nu, and mu and nu run over the dimensionality, the indices, the set of indices labeling the dimensions of the space, in this case 0, 1, 2, 3. Okay. Such a general statement is called a Riemannian manifold. Such a general space is a Riemannian space or a Riemannian manifold. Okay. In our case, in our special case where the space time is flat, what we say technically as flat, the coefficients of this of whatever multiplies dx mu dx nu, this set here, the coefficients are constants independent of the coordinates themselves. But in general you can conceive of a situation where this G mu nu is a function of the space time point, of the point labeling in the manifold itself. Then of course you do not have flat space time, but our special case has this. In general relativity, when you include the curvature of space time, this quantity will become, this thing here will become a function of the coordinates themselves. In fact, I can give an example of that in a situation, yeah, just a minute, in a situation which you are familiar with. Let us just look at a 2-dimensional space, a real ordinary 2-dimensional space, Euclidean space, but now the surface of a sphere. So here is a unit sphere, and on this sphere I have points, and I would like to label these points here. Now how do you write down the distance between 2 points? What do I mean by a distance between 2 points on the surface of a sphere like the globe? Well, one way to define the distance would be to say it is the shortest path between these 2 points. That is the distance between these 2 points, and the shortest path between any 2 points here to here would lie on a great circle, namely a circle which goes through here with this the usual great circle, like longitudes form great circles, for example, or the equator is a great circle. So between any 2 points you draw a great circle, and that distance is called the geodesic distance, or the shortest distance between these 2 points. You can define geodesic distances on other spaces as well, even if it has different kinds of curvature. Now what does this thing here mean? What does ds squared in the present case? What would this be? If this sphere had a radius r, then you would say that the distance in general between 2 points in spherical polar coordinates would be something like dr whole squared plus r squared d theta whole squared plus r squared sine squared theta d phi whole squared. This is what you would say is the distance written in spherical polar coordinates between 2 points in 3-dimensional Euclidean space. But now you are on the surface of the sphere where r is a constant, so there is no question of dr, this term goes away and you have this thing here. If this sphere has unit radius, then this r is a constant, let me remove this, it is just unit, this is it. Now you see the dx mu that I have, the x mu, the mu in this case should really run over just 2 values, 1 and 2, one referring to theta, one referring to phi. And in this case I would write this metric down in a very simple way. I would say G11 is equal to 1, G22 equal to sine theta, sine squared theta, and that is it. Pardon me? Pardon me? Yeah, G11, but I've used the fact that the superscript and subscript are exactly the same thing numerically, so this is it. And I would say G12 equal to G21 equal to 0. So you see what has happened here is that the coefficients, the g's, the components of the metric tensor, depend on the coordinate. They depend on the value of theta in this case here. Therefore this is not a flat space. Any place, any time you have a situation of this kind where these g's are constants, you have a flat space. If all the g's are plus 1, then you have a Euclidean space, but some of them are plus 1 and some of them are minus 1. The number of plus 1s minus the number of the difference between the number of plus 1s and minus 1s is called the signature of the space. And where did this minus come from? It came because the interval is c squared t squared minus x squared minus y squared minus z squared. So there is one time-like direction which contributes a plus dt whole squared, and there are 3 space-like directions which contribute minus minus minus. So I would say it is pseudo Euclidean, it is not Euclidean, it is pseudo Euclidean, still constants, so it is flat. Unlike this case where there is curvature in the space, and therefore this depends on the coordinate itself, could depend in a much more complicated way. And of course in this case, as in that case, you see that there are no cross terms, there is no d theta d phi term at all, but in general there is no reason why there should not be. In general, in a Riemannian manifold there are cross terms here, this need not vanish when mu is not equal to nu, but in this pseudo Euclidean space of special relativity this is not the case, and this is in fact the metric as it stands. Okay. Now the use of this G mu nu is that it enables you to write 2 different kinds of vectors. The moment you do not have a Euclidean space, something special happens and you can have 2 different kinds of vectors. I will explain the difference between these 2 kinds of vectors. Corresponding to this x mu, you can also define an x mu downstairs with an index downstairs. This is called a contravariant vector and this is called a covariant vector in the old literature, but I am going to use slightly different terms for it. This guy here, contravariant, this is archaic terminology. It is defined as follows, it is obtained from this contravariant vector by contracting this index nu. In other words, the convention, the Einstein summation convention is that every time I repeat an index it is summed over the allowed values, which is 0, 1, 2, 3, just like in the case of Cartesian tensors. So what has happened here is that this is G mu 0 x0 plus G mu 1 x1 etc. There is one free index mu on the right hand side and one on the left hand side, so that is okay, both of them are vectors with a downstairs index, and I call those covariant vectors. Okay. Now the real thing that is happening is that when you have a vector space, a linear vector space, you have elements in this vector space, then you can define a natural dual to this vector space which is also a linear vector space, and you can have objects in it which are the duals of the objects you have in the original vector space. They are called dual vectors, and what is really going on is that these are vectors and these are vectors in the dual space. In the language of differential forms, these are called vectors and these are called one forms. So I do not want to get into the technicalities of calculus on manifolds, which is really the right language to look at this whole thing, but we will use this somewhat old terminology. But I will not call it a vector, a contravariant vector and a covariant vector, I will just loosely call both of them vectors, or if I want to really be careful and distinguish, I will call this a vector and call this a covector. So that is a better term actually, covector, whereas here I just call it a vector on that side. Now what does this give you? This is equal to what? Well, if x mu has these components, then the question is what does this x mu have, and this is equal to G mu 0 x0 plus up to G mu 3 x3, but since G vanishes unless the 2 indices are equal, the only thing that contributes here is the 0 component here. So this immediately implies that x mu has components x0 which is also equal to x0 equal to Ct component wise, because G00 is plus 1, and it has minus x1 equal to minus x, x2 equal to minus y, x3 equal to minus z. So the covector, the space components of a covector are the negatives of the space components of the corresponding vector. Now what is the advantage of doing this? The advantage is I can write dot products in a very simple way. As you know, in a linear vector space, the only way you can form the dot product of two vectors, the inner product of two vectors always, is to take one object from the vector space, a dual from the dual vector space, and you contract the two and you call it an inner product or scalar product. Now the reason you do not see this when you do ordinary vector algebra in 3 Euclidean dimensions is because Euclidean space is self dual, and therefore it turns out that the covariant and the contravariant thing objects look exactly the same. So when you do an A dot B, you imagine that A and B are both in the same space. No, the A is in the dual space, is an element of the dual space, and the B is an element of the original vector space. But when you have more complicated objects or vector spaces, this difference is definitely there. If you are familiar with quantum mechanics, or better still, the one way to look at it is to keep this distinction is the vectors you imagine to be represented by column vectors, column matrices, and the dual objects you imagine to be represented by the corresponding row vectors. Then of course, as you know, to find the scalar you need a row on the left and a column on the right. So that is all it is. In the case of quantum mechanics, you know that these vectors are really ket vectors in some Hilbert space, and the dual space gives you the so called bra vectors, and what you have to do is to take a dot product of a bra on the left and a ket on the right, gives you a number. It is exactly the same thing with covariant and contravariant vectors. So you need to contract this object, you need to find a dot product of two vectors, you need to take a covector and a vector and dot the two and contract the two. Okay. Yeah,
is always used for a sum, right?
That is right.
But
I am going
to using it for a vector, as in the covariant vector is actually here it's four separate things, it's not a sum.
No, I am saying that this x mu, oh, good question, is this x mu a vector or is it a component is this question. So when I give you 3 Euclidean dimensions and I give you a vector, I give you a set of 3 vectors, I am going to loosely call that x mu a vector, actually it is a set of 4 quantities, that is the vector. Good point. So I am going to use a notation for it. I will loosely call a component a vector, a general component a vector, but I should not do that. I should really write x as a vector. So I will use x under bar for a vector. Then I ask what is A dot B, 2 vectors. Really I know that one of these has to be a covector and the other has to be a vector. So this is shorthand for A mu B mu, and mu summed over, just as in the Cartesian case I would write xi dot yi and call this as an x dot y. But you see this is equal to A0 B0 plus A1 B1 plus A2 B2 plus A3 B3, but my vector A mu A is really a set of 4 quantities, which is A0 and 3 space like components, which I will combine and call them an ordinary 3-dimensional vector A. B also is B0 B in this fashion, but I am going to use the same notation because there is no confusion that can arise. I am going to use the same notation for the dual vector also. So that is the reason I prefer to write this as A mu and B mu, but that is abuse of notation to some extent, because you can see it is really a set of 4 quantities and not a single component. But if I write it in this fashion, then you can also ask what is A mu, what does that comprise of, what is that equal to? This is A0 downstairs and then A1, A2, A3 downstairs indices, but we know those are minuses of the upstairs indices. So this stands for A0 equal to A0 numerically minus A minus, and similarly B mu stands for the set of 4 quantities B0 equal to B0 minus B. And now what does A dot B stand for? What is this equal to? This is A0 B0 all right, the time components get multiplied, and then this is A1 A2 A3, but those are minus of the components of A, so it is minus A dot B in the ordinary 3-dimensional sense. So you see this minus sign which was bothering us, this minus sign has been taken care of by the notation automatically. So that is the advantage of doing this whole thing. When you define a scalar product, normally you would say it is the one component of this times the one component of that plus 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 etc., but in this metric you need a minus, and that is automatically taken care of by realizing that you always contract a downstairs index with an upstairs index. So that is the rule for contraction. You cannot have the same index appear twice upstairs or twice downstairs, once downstairs, once upstairs. But it is not hard to see that this is also exactly the same as A mu B mu. So which one is downstairs and which one is upstairs is irrelevant, unlike the case of bras and kets where there is no symmetry of this kind of symmetry does not exist. In this particular space it does, because everything is real to start with. Just as an aside, you know that in quantum mechanics psi with phi is equal to phi with psi complex conjugate, but this is real vector spaces, so that distinction is not there, and therefore A dot B is the same as B dot A, and it is equal to this number here. This is a dummy index, so I can use anything I like, you can call it sigma, rho, whatever you like, it is just contracted over. There is no free index left here, this is a scalar quantity, and it is invariant under Lorentz transformations. It is of course invariant under rotations. If the time axis is not affected at all, you just rotate the coordinate axis, then this portion is not affected at all, and A dot B is invariant under rotations. So you can see this automatically preserves distances under rotations automatically, like in the case of usual 3-dimensional vectors, but over and above that it says this combination of four quantities is invariant under Lorentz transformations. So this G plays the role of lowering the index. Similarly, you can raise the index if you give me the upstairs vector. So if you give me any vector A mu and I do G mu nu, this is equal to A nu automatically, by definition this is true. Similarly, if you give me A mu and I do G mu nu, this is equal to A nu. So please notice that mu is summed over, the repeated index appears once upstairs, once downstairs, is summed over, what is left is an upstairs index, and therefore this must be upstairs in mu here. So the rules are very simple. If an index appears once, it is a free index. If it appears downstairs once on the left, it must appear downstairs once on the right. Similarly for an upstairs index. If an index appears downstairs and upstairs once, on the left hand side of the equation it is summed over, it is contracted and it is gone. If it appears 3 times, then you made a mistake. It is as straightforward as that. Now, yeah.
Conditions that a general metric tensor should satisfy.
We are not going to talk about that at all. I am not going to ask. I am not going to do that here, because I am not going to talk about general covariance, what you expect of this G, what its determinants is, and things like that. We will not discuss this at the moment. If time permits, I will come back to this. Okay, a little bit of algebra now, or let's a little bit of manipulation. What is this equal to? G mu nu G nu rho equal to. What would this be? Well, now you are contracting the mu, whatever is summed over is called an index that is contracted over, it is just contraction appears. So now whatever appears on the right hand side must have an upstairs index rho and a downstairs index mu. So it is a mixed tensor, it is neither fully covariant nor fully contravariant, but a mixed tensor in the old tensor language. Now what would this be? It is obviously a set of 16 quantities because mu goes 0 1 2 3, rho goes 1 0 1 2 3 and nu is summed over in between. But you can easily see that whatever be the values of mu and rho, this guy is 0 unless mu equal to nu, and this fellow is 0 unless nu equal to rho. So this implies that the entire symbol is 0 unless mu equal to rho, and when mu equal to rho the answer is 1, because whether it is -1 times -1 or +1 times +1 you are going to get 1 in either case. So this index, this symbol here is really the Kronecker delta, except that you must write it in this fashion. Except for that caveat that you must write it in that fashion, it is the Kronecker delta. Another way of saying it is, if I take the matrix G, if I write it as a matrix, I write the others G as a matrix, the square of this is the identity matrix, because the Kronecker delta is just a component wise way of writing the unit matrix, 4 by 4 unit matrix. Okay. What does this mean? This is equal to G by our rule, the index, by the way, G mu nu is equal to G nu mu. I have assumed this is symmetric. Then it is clear that this thing here, if I finish off the mu, it says it is equal to delta nu mu. And what is that equal to? But you have to sum over nu. So you have to sum over it, over as many dimensions as there are. So what is it equal to? It is equal to 4. So the complete contraction of this G gives you a 4. Okay. And now we begin to see how a large number of things that we write down in normal physics, in non-relativistic physics, once you include relativity, the notation, this notation makes things much more efficient to write. So let me start giving you examples. But before I do that, we need to ask also, we have a symbol for the coordinates x mu, what about the derivatives? What about the gradient operator? That is less trivial. So let us try to find that, what I mean by the divergence of something. Please recall this, please recall that del dot r in ordinary 3 dimensions stands for delta x over delta x plus delta y over delta y plus delta z over delta z equal to 3. This of course in ordinary 3-dimensional vector calculus, you know this, you take this del operator whose components are delta over delta x, delta over delta y, etc. Similarly, you can define a 4-dimensional del operator. What is delta over delta x mu? If I put mu equal to 1 2 3 etc., 0 1 2 3, then I would still expect delta x mu over delta x mu, this guy here, should be equal to what? 4, because it would be 0 1 2 3, I sum over mu, therefore this should be equal to 4, but this stands for x mu there, and I want to use a symbol for the del operator. So let me use del here and a mu here, in keeping with our convention that contraction is always done between a covariant index and a contravariant index. This is consistent provided del mu stands for a set of 4 derivatives which are delta over delta x naught, delta over delta x1, delta over delta x2, delta over delta x3, provided it stands for that, right, which is the same as saying this is 1 over c delta over delta t, because x naught is ct and c is constant, and the components with respect to x, y and z you differentiate, those 3 guys can be combined into a del. So that is very straightforward. But what is del mu upstairs? How do I define this? This by definition is g mu nu del nu. The moment I raise the index, you have to put a g out there. And what does its components become? This is equal to 1 over c delta over delta t. This remains unchanged, but we know that the spatial components g1 1 2 2 3 3 are minus ones, therefore this is a minus. You must remember this, this is important, because it says del mu equal to delta over delta x with a mu downstairs here, it is the derivative with respect to the covariant vector here components, and that has a minus sign here. Contrast this with, so let me write it just to emphasize this, x mu equal to Ct or del mu equal to 1 over C delta t, delta over C delta t minus del, but x downstairs is Ct minus r, del downstairs is delta over C delta t plus del. So this you have to remember, that del mu if it is put downstairs has a plus del, whereas x mu if it is put downstairs has a minus r, and it is inverted there, and this is obvious because of what I showed you, namely delta x over delta x is plus 1 by definition. So with this caveat, we can now start writing down all the rules that we know, all the laws that we know in relativistic form, provided we identify the right quantities always. So first, what is x dot x equal to? This stands for x mu, and as you know this is c squared t squared minus r squared in a given frame of reference. You are familiar with the fact that the energy and momentum of a relativistic particle are related to each other by a relation free particle, which is different from the one which you have in non-relativistic mechanics, and you in fact know that the relation is E squared is c squared p vector squared plus m squared c4. Let me just call m the rest nice, this relation, and dimensionally you would like to have quantities of dimension momentum everywhere, just as I put a c here to make sure that the time component of the vector has exactly the same physical dimensions as the length as the space like components here. In exactly the same way you divide by a c squared, and this relation is this Of course this immediately suggests that this equal to that is an expression of relativistic invariance, and indeed it is. The definition of the 4 momentum p mu is equal to E over C p. The covector is therefore E over C minus p, and that helps you to identify what this quantity is. This thing simply says that p mu equal to m squared c squared. That is the correct energy momentum relationship for a free particle, written in manifestly covariant form. P mu is a Lorentz scalar, so it is exactly the same in all frames of reference, and its numerical value is equal to the square of the mass multiplied by c squared. So this is the covariant way of writing this, namely the way that shows explicit Lorentz invariance, because this guy here is a scalar, Lorentz scalar. Similarly, you look at some more rules here. We know that the charge density and the current form a 4 vector current J mu. Together these are the natural quantities that combine to form a 4 vector current. Then what is this? What is del mu J mu equal to? It is the divergence, the 4 divergence of the 4 vector current, and this stands for delta over 1 over C delta over delta t of 0 plus, that is important, del mu downstairs is a del operator dot j, and this is equal to delta rho over delta t plus del dot j. And the equation of continuity says that if there are no sources and sinks in a given region, then this quantity is equal to 0. But that is just an expression of the fact that the 4-dimensional current, the 4 current is divergenceless. But since that is a Lorentz invariant statement, the equation of continuity is valid in all frames of reference, and as you know it leads to charge conservation, and that shouldn't depend on the frame you are in. So this explicitly shows that a concept like charge conservation is Lorentz invariant, it is the same for all frames. So if charge is conserved in one frame, it is conserved in all other frames as well, and this is a very simple way of writing the continuity equation. In the same way, it turns out that you can define a 4 vector potential, and that is equal to phi over c, the 3-dimensional vector potential. So these two combine, it turns out, the scalar potential and the vector potential in electromagnetism into the components of a 4 vector potential. The 1 over c with phi sees to it that they have the same dimensions, physical dimensions. Then notice that we talked about the Lorentz gauge, and the Lorentz gauge condition was 1 over c squared delta phi over delta t plus del dot a equal to 0. It might have struck you that this is a very strange combination, because I said once you put this condition in, then the quantity A obeys the vector potential A obeys the wave equation, a very simple wave equation. But it might have struck you that this combination is very strange, but that is not a strange combination, because this thing here is really just del mu A mu, because the 1 over c delta over delta t is del 0 and phi over c is a 0. So it is del 0 a 0 plus del 1 a 1 plus del 2 a 2 plus del 3 a 3, that is del mu a mu. So this is the Lorentz gauge condition, del mu a mu equal to 0, very compact way of writing it. And since it is a scalar under Lorentz transformations, it says the Lorentz gauge condition is Lorentz invariant. Even if you change to another frame, you are still in the Lorentz gauge. That is no longer true if you are in the Coulomb gauge, where del dot A alone is 0, then this does not transform like anything simple under Lorentz transformations. This gets mixed up with the time component and it is no longer covariant. So the equation of continuity turned out to have a very simple form, the Lorentz gauge condition turned out to have a simple form. The question to ask is, what does the Maxwell equation itself look like? Does it become simple or not? Well, before we do that, let us ask what the Laplacian does. So we could ask, what is this quantity, del mu del mu? That is a 4-dimensional analog of the Laplacian operator. This stands for second order partial differential operator. So this is equal to del 0 which is equal to 1 over c squared delta 2 over delta t2 minus del dot del, minus because the upstairs guy is minus gradient and this is plus gradient here, operator here, but this is equal to 1 over c squared delta 2 over delta t2 minus del squared. That is the wave operator, okay, and it emerges naturally, as you can see. This has got a name, since it appears all the time, it is written as box, and it is called the D'Alembertian. It is written in this simple form. And now of course we know that if something obeys the wave equation, it is a scalar quantity, this minus del squared equal to 0, then it says box on that equal to 0, that is a simple thing. But we know that the Maxwell equations themselves, the two that are left after you get rid of the after you eliminate things in favor of the scalar and vector potentials and you go to the Lorentz gauge, the Maxwell equation gave you one for phi for the scalar potential and another equation, the wave equation, for the vector potential. For the vector potential you ended up with 1 over c squared d2 over dt2 minus del squared on the vector potential A equal to j in some units, I do not recall the units now, but maybe a mu naught here or there, but times j in this fashion. And similarly there was an equation for phi. Now verify that both those equations can be combined and the equation is just box A mu equal to j mu, that is it. that is the set of Maxwell equations, all of them. So once you go to the Lorentz gauge by imposing this condition, then the Maxwell equations simply say, in free space, simply say D'Alembert on A mu equal to J mu. This is the source and that is the field, that is it. Of course you got to go back and look at what happens to E and B, and E and B are 3-dimensional vectors, they do not look anything like this at all. So we still have to answer the question of what to do about E and B, which we will talk about in a minute, but I want you to appreciate the fact that this is a manifestly Lorentz invariant way of writing Maxwell's equations, because every quantity that appears here has known transformation properties under Lorentz transformations. This is a scalar operator, that is a 4 vector, that is a 4 vector there, and this is a scalar quantity here. So it is called the manifestly covariant form of Maxwell's equations. In fact, we can go a little further. We could look at this equation here, this guy here, and put in a little quantum mechanics and look at what is going to happen. We are jumping a little bit, but we put in a little quantum mechanics. As you know, in quantum mechanics you can't describe particles by trajectories, you have to use wave functions for them. There is a certain fuzziness associated with things, but these physical quantities like energy, momentum and so on become operators which act on the wave function. So let us see where this gets us. Remember that the classical to quantum correspondence says that the energy, or better still the Hamiltonian, is replaced by IH cross delta over delta t. So this physical operator called the Hamiltonian, when it acts on a wave function, it is like acting on the wave function by IH cross delta over delta t. On the other hand, the 3 momentum is minus IH cross the gradient. These are the standard correspondences which you learn from the Einstein-de Broglie relations, for example. Once you do this and you act on a wave function, you get the wave equation, the Schrodinger equation, for instance. Now we are trying to do this in the relativistic case, so we would like to do it here. This E stands for the Hamiltonian, it is the energy here. So what does this tell you? Together these two guys, since this is E over C times E, these two guys correspond to saying that you have the correspondence P mu goes to minus P mu goes to IH cross del mu. That is the correspondence. But please notice that the change in sign is automatically included. There is a plus here and a minus here, but that is already here because it says the space components give you IH times the space components of this del, but there is a minus del. So this has already been included there. Then this relation here, when I go to quantum mechanics, should really be written minus IH P mu del mu. That is it. I just lower it putting the G and it gives me an IH cross del mu. So this says IH cross del mu, IH cross del mu on a wave function, let me call it psi, equal to m squared c squared on a wave function psi, which is now a function of space and time coordinates. This would be the relativistic wave equation for a free particle, a free relativistic particle. And where does that get you? This gives you a minus sign, so let us bring it over to this side and it says del mu, that is box on this side, plus m squared c squared over h cross squared on psi. So that is the free quote unquote Schrodinger like equation. This equation has a name for a relativistic particle, it is called the Klein-Gordon equation. What is the physical meaning of mc over h cross or h cross over mc? This has dimension 1 over length squared because it has a del squared in it. So h cross over mc has dimensions of length mc is what you would call the Compton momentum of a particle, and h cross over mc by the de Broglie relation is the Compton wavelength. So this is the Compton wavelength. To the extent that you can associate a size with a quantum mechanical particle, this is the natural size and this is the Compton wavelength. What happens if you put m equal to 0? You get boson phi equal to 0, but that is exactly the equation here. In free space, in the absence of sources, you get boson a mu equal to 0, but then of course unlike a scalar function phi, you have a vector function a here. So you have 4 equations here. Those are the free electromagnetic equations, they describe electromagnetic radiation. And the reason you need a vector index there is because electromagnetism is described by 2 vector fields E and B, and not by a single Lorentz scalar field which has only 4 components. So therefore this thing here is only an auxiliary potential, but you need more than one component, and it turns out you need, for technical reasons, you need 4 components here. There are other ways of doing this, but this a mu describes the electromagnetic field from which you can derive the electric and magnetic fields, and it satisfies boson a mu equal to 0 to describe radiation. So when m goes to 0, you end up with an equation just says boson psi, this quantity equal to 0. So Maxwell's equations, which would describe, which in the case of the source free region would be pure radiation in the absence of sources, would describe massless particles, particles of 0 rest mass. So it is consistent to the fact that the photon has 0 rest mass. Once you remove this, it is gone, and then you have this free equation here. Of course you could ask, what are E and B? And this is not a very trivial question. It is not immediately apparent how to combine things, but once we know what del does, it is not so hard. Remember that B was equal to del cross A, and you had E equal to minus delta A over delta T minus grad phi, that is something like this, and these two equations do not look like anything like each other, they are very, very different things. Of course we got it in a straightforward way from Maxwell's equations, so you should ask, why do Maxwell's equations have the form that they had there, but you already know that once you do things relativistically, Maxwell's equations start looking very, very symmetric. Therefore it is natural to expect that this condition also is some very simple kind of condition here. This is a curl condition here, but if I write this out, if I write this out in terms of vectors and things like that, it says B, any component of it, let us call it Bi, I now put superscripts on these guys, equal to, it is a cross product here, so we should really be careful here, this is equal to del I, del, well, we write this out explicitly, so Bx equal to delta over delta y Az minus delta over delta z Ay and cyclic permutations, and similarly Ex has a space component of A differentiated with respect to a time component of x mu, and then the time component of x mu differentiated with the space component of the del operator. So it suggests this is also like a curl, it is mixing things up, and indeed what you can do is to define a tensor f mu nu definition as del mu a nu minus del mu a nu. Define an electromagnetic tensor of this quantity, it is a rank 2 tensor, and by definition it is antisymmetric. Similarly, of course, you can also define f mu nu equal to del mu a nu mu minus del mu a nu. That just contracts this guy and lowers it here. And then, and I want you to do this given the definition of del, given the definition of the 4 vector potential a mu as phi over c a, and the del operator as 1 over c delta over delta t and minus del, I want you to show that this f mu nu, which is a rank 2 4 by 4 4-dimensional tensor has how many independent components? Well, since mu and nu to start with run 0, 1, 2, 3, there are 16 components here, but many of them are 0, the diagonal ones are all 0. So how many independent components does it have? There are 16 components, 4 on the diagonal are gone, that leaves 12, but it is antisymmetric. So the 6 below are written in terms of minuses of the 6 above, and therefore it has 6 independent components, and indeed 6 is precisely the number of components you have for 3 electric field components and 3 magnetic field components. So this is going to give you fully the electromagnetic field. So apart from signs and so on, I want you to show that it zeros here, and then there will be Ex, Ey, Ez here with minuses here, and then B. I do not remember whether this is a 2, 3, so this is going to be a Bx, this will be a minus By and a Bz in the standard way of writing it, this form. Give or take some signs and so on and so forth, this is what would happen to the F mu. Okay. So I leave it to you as an exercise to complete this, to write out this tensor explicitly and write out F mu nu also completely, the downstairs F mu nu also. This would interchange, these fellows would become minuses and these would become pluses, and there will be some changes here. Time space components of the electromagnetic field tensor, this F mu nu is called the electromagnetic field tensor, give you the electric field, and the space components give you the magnetic field completely. Once you have that, you can ask what quantity, what combination of E's and B's remains unchanged under transformations, under Lorentz transformations. What quantities E and B do not remain unchanged, and we are going to write down very shortly the transformation properties of electric and magnetic fields. This is immediately obvious. I have a charge here and I am at rest with respect to it, there is no magnetic field, I see an electric field, an electrostatic field, but I start moving with respect to it, to me it is as if this charge is moving and producing a current, and therefore I see a magnetic field. So you can immediately see that electricity and magnetism are closely linked, and under Lorentz transformations you can expect electric fields and magnetic fields to get mixed up and go into each other, but there are some quantities which would remain unchanged, and you can guess what that quantity is. Given this as F mu nu, you can construct several invariants and check which of them are independent. It is immediately clear that F mu nu is a Lorentz scalar. So I want you to write this matrix out, the two matrices out, multiply them and check out what combination is invariant. Incidentally, you should be a little more careful. I have used the units that are most natural here in terms of C, but if you go back and write the Maxwell equations in terms of mu naughts and epsilon naughts and so on, then you have to be a little careful in writing these components. So there will be various mu naughts and so on sitting here, which are a little uncomfortable, but whatever it is, once you fix those units, I want you to check out what that quantity is, F mu nu, F mu nu. Okay. Do you think it is the energy density of the electromagnetic field? Do you think it is, what is the energy density of an electromagnetic field? Electric field E, magnetic field B. Well, in the units that you people use, the standard international units in free space, it is equal to half epsilon naught E vector squared plus half mu naught B vector squared, right. This is what you would call the energy, this is the energy density of the electromagnetic field. Would this be the same in all frames of reference, do you think? What do you think? Well, I would say no, because based on the experience with particles, where I know the energy of a particle is not Lorentz invariant, right. That is immediately true even in non-relativistic mechanics. The kinetic energy of a particle is not Lorentz invariant. If it is a free particle, it only has kinetic energy, but if I start moving along with it, it has no kinetic energy in that frame, if it is moving at constant speed. So it is clear the energy is not an invariant, it is the time component of a 4 vector. In the case of the electromagnetic field, the energy density is the 0 0 component of a rank 2 tensor, and therefore it is not invariant, and yet some quadratic function of e's and b's is invariant. As you can see, it has got to be a quadratic function, because this fellow has e's and b's, this guy also has e's and b's, and when I multiply these two matrices I am going to get some combination of e's and b's everywhere. So I leave you to work out that Lorentz scalar, and we will discuss that tomorrow, what the scalar is. It will turn out to be not e squared plus b squared, but e squared minus b squared, and that is invariant. So end up with a minus sign here, and it has a significance. It is the Lagrangian density of an electromagnetic field. So that is the density from which you can derive Maxwell's equations by using the Euler-Lagrange prescription, and that is the same in all frames of reference. So the Lagrangian density of a field is invariant, Lorentz invariant, but the Hamiltonian density is not invariant. There is another constant here which is exactly the same, and we will discuss that as well. You see, what looks like light in another frame also. It should, because we started off by making the postulate of relativity. So if I have electromagnetic radiation in one frame, another inertial frame, it should also be an electromagnetic radiation. Now what is characteristic of the electric and magnetic fields of electromagnetic radiation? What sort of wave is it? Transverse waves. What does transverse wave mean? There is a direction of propagation, and what about E and B? They are perpendicular to each other. So the fact that they are perpendicular to each other must remain unchanged. Now how do you state the fact that E and B are perpendicular to each other in terms of vectors? The pointing vector gives you the direction of propagation. E dot B is 0. E dot B is 0. So E dot B equal to 0 must be a Lorentz invariant statement, even though E and B themselves change. This is only a 3-dimensional scalar, but the fact that it is 0 must somehow be a Lorentz invariant statement, and it will turn out that the other invariant that you can write down from Maxwell's equations is E dot B whole squared. That quantity is invariant, and if it is 0 in one frame, it is 0 in all frames. So E dot B whole squared is the other quadratic invariant you can form from a Lorentz invariant scalar that you can form from the electromagnetic field, and we will discuss tomorrow the transformation properties of electric and magnetic fields that tell us how these fields change when you go from one frame to another, and how these two constants, how these two Lorentz scalars appear, how this guy appears, and how the Hamiltonian density, the Lagrangian density appears. We will look at that next time. So the physical interpretations of these are important, because it tells you that radiation looks like radiation in any other field. You could also ask, are there other invariants? Is there anything else? And we will prove that there aren't any more. There are just these two fellows, two quadratic combinations of E's and B's, which are Lorentz invariant, with specific transformation properties for the E's and B's themselves. Finally, looks like there are two different ways of describing the electromagnetic field. One is in terms of a vector potential, which has 4 components, and the other is in terms of a rank 2 tensor, which is antisymmetric, which has 6 components. This is exactly like saying, once you give me A and phi, I give you E and B, because these guys have specific curls and relations and so on. So there too you have two different ways of describing it, and you could ask which is more fundamental, are they equivalent, and so on. These questions assume a great deal of relevance in quantum mechanics, and perhaps later on in the quantum course I will describe how this is connected to the question of spin and representations of the Lorentz group, how these two equivalent ways of describing this spin 1 particle each has its own physical significance. We will talk about that at this stage. Just one last point, and that is, when you write the interaction between an electromagnetic field and a charged particle, that too should be writable in an invariant form, in exactly the same in all frames. And it turns out that the thing that leads to, we wrote down the Lagrangian of the charged particle, and you could ask, where did this Lagrangian come from? I tailored it to get the correct Lorentz force equations, but really I must go back to fundamental principles and say I must find something that is invariant, Lorentz invariant. So the equations look the same in all frames of reference, and then the interaction Lagrangian should have something which depends on the field and should have something that depends on the particle. The thing that characterizes the field is the 4 vector potential, and I need something to contract it to get a constant, to get a Lorentz invariant quantity, a scalar, and that is J mu. It is linear in this, it is linear in that, and this is the simplest thing that will couple the two, and it is called minimal coupling. You are familiar with it as Ampere's theorem. This is Ampere's theorem, just minimal coupling here. So this is the coupling that is used, and now of course the proof of the pudding is in the eating. One puts this in and uses the rules of relativistic quantum field theory to see if you get correct predictions, and the answer turns out to be yes, this is the right Lagrangian in this case, not any more complicated thing in terms of f mu nu, etc. Okay, so let me stop here, and tomorrow we will start off by writing down the equations, the electric and magnetic fields in terms of the field tensor f mu nu, after which we will look at the f mu nu and see what happens if you contract it and so on, and then we will write down the Lorentz transformation properties.